So, good morning, everyone. Actually, today we are going to learn about some basic concepts of linear transformations. Before itself, we should know about the vector space. The main concepts are the vector space. So, vector space. And next, you should know about the subspaces. And next, linearly independent. And next is a linear span. Linear span. If you know about these four concepts, you can clearly go to the concepts of linear transformation. So, first of all, we should know about what is our vector space, subspace. I'm leaving this concept for your concentration because you're going to study by your own or refer some other videos. I'm going to start from the linearly independent, linearly dependent. Okay, so linearly independent, linearly dependent means first of all, the let V1, V2, and so on, Vn are the vector space or the vectors from a vector space, and alpha 1, alpha 2, alpha 3, or and so on, alpha n are the scalars. Okay. Then the linear combination alpha 1 v1 plus alpha 2 v2 plus and so on plus alpha n vn equal to 0. Then we have to prove that alpha 1, alpha 2, and so on, alpha i's, that means alpha n, equal to 0 for every I varies from 1 to n. Then v1, v2, and so on, vn are linearly independent. Okay, so what is a concept is you're having v1, v2, and so on, vn vectors from a vector space, any vector space it can be, and alpha 1, alpha 2, and so on, alpha n are the scalars from a field. If you're writing that alpha 1 v1 plus alpha 2 v2 and so on plus alpha n vn equal to 0, alpha i's are 0 for every alpha, then that vectors are called linearly independent vectors. Suppose sum of the alpha I is non-zero, it means that one alpha is depending upon other alpha. That means it is dependent. Okay, that means our vectors are dependent. So now you clear about linearly independent. Okay, now we are going to see about the concept of linear span. Okay, what is a linear span? Here, for linear span, we are just using the set, that is linear span. Linear span, when you're writing linear span, you have to use this notation L of S, which is equal to set of all. That means before itself we have to define S set. What is your S set? S set is a set of vectors. It can be any vectors. It should not be, it need not be a linearly independent or dependent vector. It can be any vectors. Okay. So now I'm just writing the set L of S as alpha 1 V1 plus alpha 2 V2 and so on plus alpha n Vn. Okay, such that alpha I belongs to a field. Okay, here what you're doing is there in linearly independent we have write just alpha 1 v1 plus alpha 2 v2 and so on alpha and vn without a set bracket. But here we are using set brackets and also we are varying the alpha i's in the scalars, set of scalars. Okay. So if you're writing this set, this can be say linear span of a set S. Okay. Okay. Next concept, we should know about what is basis. Okay. Basis. A basis is nothing but we have studied two concepts, right? So a set B is said to be a basis if it should satisfy the set, it should satisfy that linearly independent set Okay. And second one is linear span equal to whole vector space. Okay. If these two conditions are satisfied, then we can see that is linearly, that concept involves linearly independent set and linear span equal to V, then we can say that the set is a basis of a vector space. So now I'm going to give example of basis. Okay. So we have studied three concepts theoretically. Now we will see some examples of that. So actually now the example of linearly independent set. Okay. Linearly independent set. How we can, I'm giving one set S equal to 1, 0 and 0, 2. Is this linearly independent? Your vector space is R2 over R. Okay, R2 over R. How can you say that? So first of all, we have to write that linear combination. What is linear independent means? We have to write a linear combination alpha 1 v1, alpha 2 v2, and so on alpha n vn, right? Equal to 0. So here I'm writing this in S set. I'm taking v1 as 1, 0, v2 as 0, 2. Two vectors only we are having. So how we can write it? Or we can write it alpha 1, v1 is 1, 0 plus alpha 2, v2 is 0, 2, which is equal to 0. That means 0, 0. In R2, 0 is 0, 0. Okay. So now, how we can solve this one? You just multiply. So with alpha 1 with the first term and alpha 2 with the second term. So that means we are having 0, 2 alpha 2, which is equal to 0, 0. So now how can we solve? Finally, you're having that. Add two vectors alpha 1, 0 plus 0, 2 alpha 2. So we are having alpha 1, 2 alpha 2, which is equal to 0, 0. So here I am just equating a first component, that is alpha 1 equal to 0. And next I am just equating second component, that is 2 alpha 2 equal to 0. So alpha 1 equal to 0, 2 alpha 2 equal to 0 means alpha 2 equal to 0 by 2, so that means 0. So here alpha 1 and alpha 2 both are 0. That's why this set S can be called as a linearly independent set. Okay, this S is linearly independent. So can you understand? So now the next concept is linear span. Okay, linear span is, I'm going to give a same set. Yes. How can you find the linear span? That is my question. How can we find it first? So now let me erase this one. Okay. So now I'm going to write the same set S equal to 1, 0, 0, 2. So we know that this set is linearly independent. If we write, if we verify that whether the set is linear span, that means linear span equal to V, then we can say that this set is a basis of R2, right? So to check linear span, alpha 1, linear span is a set, right? We have to put it in the set bracket. Alpha 1, V1. That means V1 means 1, 0 plus alpha 2 into 0, 2. Such that what you have to write here is such that alpha 1, alpha 2 belongs to field. Okay. Now, what is your set? How can we see the set, Pa? How can we write it as the set of all? The next step is set of all alpha 1 plus 2 alpha 2. That means alpha 1 here, alpha 1 comma 2 alpha 2 equal to 0 0. Okay. Now alpha 1 alpha 2 belongs to a field. Here field is a real number. Okay. So this set, you just check whether this set generate the vector space R2 over R or not. Here alpha 1 alpha 2 belongs to a field. That field is nothing but real number. So the set forms, you just check whether the set forms the whole vector space R2 over R or not. That's my question. How we can say this? How we can say is, we can tell that the set alpha 1, comma 2, alpha 2, alpha 1, comma alpha 2 belongs to real number. So, which is equal to R2 over R, which is equal to the whole vector space. Okay. So, now we can tell S equal to 1, comma 0, 0, comma 2 is a basis. Basis of what? Basis of R2 over R. Okay. Clear. So, can you tell some other basis of R2? Some other basis of R2, can you tell that? How can we tell that one? I am giving one more set. Just practice, that is, just check whether that is basis or not. S equal to 1, comma 0, 0, comma 1. That is 1, comma 0 and 0, comma 1. Now, the you have to check this. Take it as a homework, and also here you have to check 1, comma 0, 0, comma 1 also you can check. Okay, these two sets, you just check whether one is 1, comma 0, 0, comma 1, and another thing is you can change here 1, comma 1. Okay, so one set is 1, comma 0, 1, comma 1, and another set is 1, comma 0, 0, comma 1. Okay, take it as a practice problem. Now I am going to now I am going to a linear transformation. Okay. So first of all, linear transformation. What is the definition of linear transformation? How can we tell that? Let V, comma W be a vector spaces. T, a map T. Okay, a map T from V to W is said to be a linear transformation if it follows two conditions. First condition is T of U plus V equal to T of U plus T of V, and next condition is T of alpha U equal to alpha of T U, where you should know U and V belongs to V and alpha belongs to scalar. If this two conditions are satisfied, then you can say that map is linear transformation, that is linear map. Okay. For example, I'm giving one example for you. I'm writing a vector space, that is V equal to R2, W equal to R2. So, I am giving a map. T is R2 to R2. The map is T of x comma y equal to x comma 1 plus, not 1 plus y, just y. Okay. This is the identity map, right? We will check whether this map is linear or not. What is the condition first we have to take? Here u you have to tell. What is your u? Here v is R2. So u is a vector from R2, that is R cross R. That means a tuple. You can take x1 comma y1 and v equal to x2 comma y2. Okay. Now, what is the first condition? T of u plus v. T of u plus v means T of u is x1 comma y1 plus x2 comma y2. This is another vector. And again, one bracket. Here also you are having brackets. That means you have to add the vectors inside the brackets. That means x1 plus x2 comma y1 plus y2. This is component wise addition. Okay. So now you can consider this first term as x, second term as y. How can we substitute in this formula, linear map formula? The first component here we are having just x in the place of x, and we are having y in the place of y. That means first component is going to a first component is the map, and second component is going for the second component of the map. So that similarly we can write the first component is x1 plus x2. So we are having, and second component is y1 plus y2. So now we have this one as a map. Now we are going to find the right hand side of the first option. We just have this one. Left side we have completed. So now this is the left side. This is the right hand side. I am going to write. What is that right hand side? T of u plus T of v. What is T of u is? You have taken x1, y1 as u plus T of v means x2 comma y2. Here you are having two maps. That is T of x1 comma y1 means when you are applying the map you will get, what you will get? x1. First component is in the first position and second component in the second position. I have applied. And in plus, second one is T of x2, y2. So that means first component is a x2, right in the first position. Second component is the y2, right in the second position. So finally, you have to add these vectors. What you will get? x1 plus x2, comma, y1 plus y2. So we are having right hand side equal to left hand side. So first option is satisfied. First axiom is satisfied. So that's why we can say that first option is satisfied. So second, we can go for the second option. We'll check what will happen for the second option. Okay. Now map is T of x comma y equal to x comma y. Okay. So second option is t of alpha into u. You have considered as u as a x1 comma y1, which is equal to t of, I'm multiplying alpha with each components, alpha x1 comma alpha y1. So now we have to substitute the map. What is your map? So first component is alpha x1. I'm writing in first component. And second component is alpha y1. Writing in a second component. So this is your left hand side. And I'm going to write a right hand side. What is the right hand side? Alpha into t of u. What is that? Equal to alpha into t of u means you have taken x1 comma y1 equal to alpha. What is your map? X1 comma y1. So now I'm going to multiply alpha on both sides. X1 plus alpha y1. Finally, here also, sorry, x1 comma y1. Finally, here also we are having right hand side equal to left hand side. That's why the map is linear. Okay, if both the conditions are satisfied, we can say that the map is linear map. Okay, so ma'am, what are the properties of linear transformation, ma'am? From the linear transformation, what can we find extra? That means that is we have more concepts based on the linear map. So we can try one more problem. The problem is T is R22 R3. R22 R3. R22 or we can try. Okay, R power 1. So T of x comma y will goes to 1. Which is a simple map. Can we check if this is check whether this is linear transformation? What's our first option? That means T of u plus v equal to. So as last problem, we have to take x1 comma y1 is a u and x2 comma y2 is a v. Okay, which is equal to, here we are having parenthesis. Here we are having t of, just add inside the vectors x1 plus x2 comma y1 plus y2. So anyway, the map is equal to 1. Here, whatever is the left hand side, the resultant is 1. Because this map is like that. So we have to substitute t of x1 plus x2 comma y1 plus y2 equal to 1. Okay. Now, the trick is, this is the left hand side. Right hand side, what you have to do? T of u plus T of v equal to T of u is nothing but x1 comma y1 plus T of v is nothing but x2 comma y2. So in this problem, I'm not writing uv. I just took that value similarly as last problem. Yeah. Okay, here T of x1 comma y1. By this map, we are having 1. Okay. And next, plus T of x2 comma y2. By this map, we should get 1. Anyway, we are getting 2 here. In the left hand side, we got 1. But in the right hand side, we have got 2. So that means 1 not equal to 2. So this map T is not linear. Okay. Can you understand? Like this, we can conclude. Okay, now we are moving to a next concept, that is range space. So before going to range space, I have to tell about dimension. Dimension is nothing but the number of element in a basis. Okay, this is simple. Okay, suppose suppose basis. In last problem we have seen that s equal to 1 comma 0, 0 comma 2. This is the basis. We have proved that, right? What is a dimension? Dimension of R2 over R. We have proved that this is the basis of R2 over R. So what is the dimension of R2 over R? Number of elements in a basis. Here in this set, two elements are there. So that's why in the basis two elements are there. So the number of elements in a basis is 2. So dimension of R2 over R is 2. Okay, it's a simple concept. Now we can move for the next concept, range space. Range. Usually, what is a range? We already know that usually range is a image, right? Image of one map. So we are having domain, we are having codomain. This is the map. It is going from V to W. It's a one. V is a vector space and W is another vector space. It need not be same. U and W are need not be same. If we are applying one map, this map, for example, t of x comma y is going to x comma y. Then this x comma y, what are all the elements from V is mapping to the element W? It's called the collection of that elements called the range. Okay. Here you are substituting some element from a domain in a map T. You are arriving with some element in a W. You are arriving with the element in a W. That elements or set of all that elements are called a image or range. Okay. So how can we write it as a set bracket range of T? That means range space of T. You are going to collect T of X such that X belongs to V. Okay, this is the set of range space. Okay, I am giving some map for you. You are going to find a range space of this. T of x comma y comma z equal to x comma y. How can you say this? This map is from which vector space to which vector space? Here 3 tuples we are having. That means R3 over R. It's going to right hand side. The tuples is 2. So it is mapping to R2 over R. So map is from R3 to R2. What is the range space? What is the definition of range space? In this slide, above step is the set of all T of X. Here, the set of all T of X. The set of all T of X such that X belongs to V. Right? So here we are going to find the range space of T. Here T of X. X belongs to V. So V is here. What is here V? R3 is V. W is R2. Now, set of all T of X belongs to V. V is R3. So, here you have to write a 3 tuples. If it is V is R2, you have to write a 2 tuple. Okay. So, such that X X means you have written X comma Y comma Z instead of X. So that's why you have to write X comma Y comma Z belongs to R3. Okay. Now, to find the range space of T, just substitute your map. What is your map? Map is T of X comma Y comma Z is going to X comma Y. You are substituting 3 tuples, but it is resultant with your X comma Y, only 2 tuples. So, like that, X comma Y belongs to R. Okay. Now, what is your range space? So this is your range space. Finally, you have substituted map. You have arrived with this set. So this is the range space. This is the range space. Okay. So how to check? In the next step, we are going to find a basis for this range space. A basis for this range space. How can we find? We can see. You have finally have arrived with R of t equal to X comma Y. That's it. Such that X comma Y belongs to R. This is the final step we got. Here, I am going to find the span of just take X out. In first tuple, we are having X. So just write 1. Comma. Second tuple, we don't have any X. So just write 0. Plus. Now I am taking Y outside. In first tuple, we don't have any Y's. So just write 0. In second tuple of a set, we are having only 1 Y. So just write 1 Y. Such that X comma Y comma belongs to R. Okay. Now, what are all the vectors? Spanning set. How can we write a spanning set always? Alpha 1, 1 comma 0 plus alpha 2, 0 comma 1. In place of alpha 1, alpha 2, we are having 1 X comma Y. That is no problem actually. Next step, in the place of V1, V2, what we are having? Vectors 1 comma 0, V2 is 0 comma 1. Just write S equal to 1 comma 0 because we have arrived with 2 vectors, that is 1 comma 0, 0 comma 1. That vectors I am going to put it in one set. So that set is equal to linear span of S equal to R of t. Why this is possible? Because we have spanned this set from the range space only. Okay. From this set only, from this R of t set only, we have arrived with this final step. We got V1, V2 from R of t. So, these two vectors V1 and V2 only spanning the before set, that is R of t. That's why S is a spanning set of R of t. Okay. If you find a spanning set of 1, 0 and 0, 1, we can get R of t again. So, the second condition of basis is satisfied. Now, we should go for the first condition. Okay. What is your first condition of basis, Pa? A first condition of basis is nothing but linearly independent set. So, S equal to, finally we got 1, 0, 0, 1. We got this set is linearly spanning set. but linearly independent or we have to check. Alpha 1, 1 comma 0. What is the condition of linearly independent? Alpha 1 V1 plus alpha 2 V2 equal to 0 comma 0. Finally, we are getting alpha 1 comma alpha 2, which is equal to 0 comma 0. Okay, here if we equate each tuples, alpha 1 equal to 0, alpha 2 equal to 0. So when both the alphas are 0, then you can say this set S is linearly independent. So what is our conclusion? Why we are finding this? We have concluded is S is a basis set. From which set we have got this S? From R of T. So this basis, S is a basis of R of T. So what is the dimension of R of T? You can tell now. What is the dimension of R of T? So dimension of R of T is nothing but number of elements in a basis. So a basis of R of T is now 1 comma 0, 0 comma 1. So two elements are there. So cardinality of S is 2. So basis of, dimension of R of T is, what is dimension of R of T? Number of elements equal to 2. So now I hope you all understood this concept till range space, how to find a dimension of range space. So thank you.